So let's get this done now. 27th, 227th question. This was kind of hard because I didn't have any information about what's actually happening. Now I do. So go watch those two videos that I uploaded, right? Yeah, so what was it, right? One of them was like damped elliptical motion, right? That was kind of a title. And the other one was just another, uh, yeah, video where it was not for an elliptical orbit but for a circular orbit. Anyway, the thing is, now I know how to do this thing. So because your alpha is so small, what we can do is assume that every time you actually complete a revolution, throughout the revolution your orbit is almost circular, right? So first it was going in a circular orbit, and now, right, it gets through some kind of space dust, then it slows down a bit. I know it's not exactly circular anymore, but it is almost circular. And then, right, so it's, you got the moon over here. It's not a point object, but think about it. You got the moon over here. This is our satellite. It's going in a circular orbit like this. Yeah, but now what happens is that it gets some space dust in its way, and now it, instead of going like that, goes like this. So it ends up over here, right? So its r value is smaller now, but the velocity is still pretty much just perpendicular. I know there's a component, but ignore that. The thing is, its a is changing at a rate which we can figure out, right? I shouldn't say a, I should say the r value. So the radius of the orbit is changing at some certain rate. We know that these are orbits are actually not circular. These are just spiraling down, right? It's not circular, but assume it is for now. So what do we have? The force is alpha v square, right? So that times the velocity is going to be our power, or a negative power, whatever. So alpha v cubed, right? I guess that makes sense. And this thing will just be equal to our d upon dt of energy. And energy is, so we calculate the stuff, right? So for, yeah, the energy, total mechanical energy is just negative gmm. It should be upon 2a, right? Not upon a, it should be upon 2a. I mean, we also calculated this somewhere else. Just wait a second. It will be somewhere. No, not this one. Oh yeah, this thing. So it's upon 2a, not a. Anyway, that's the thing. And also, by the way, I should actually inform you that this omega I'm using all of the time is actually the average angular velocity. So not the angular velocity. But for circular orbits, it's the same because, yeah, it's not changing. The a value is not changing. The r value, right? That's what I should say. The r value is not changing. It's just constantly a. So, right, that works out. And let's do the thing. So alpha v cube, that is how fast the energy is changing. But the energy is just negative gm upon 2r squared. Oh, sorry, just 2r, not. And that is also, right, it's not squared, I think. There too, it's probably the same stuff. Where did that go? Uh, oh yeah, this thing. So that's right. Gmm upon 2r, right? That's energy. The derivative of this thing, that will be like this. So just equate these guys, and there we go. And of course, you also need a dr upon dt stuff. So yeah, this should work out. Or maybe not. Okay, think about it. You want, okay, the work done by this space just on this, it's actually negative, isn't it? Because dr upon dt is also negative. So that's why this equation should be like this thing and not positive everywhere. That makes sense. Okay, so what do you got? You got dr upon r is equal to 2 alpha, actually negative 2 alpha, right? Okay, and then upon gmm, and then you got this v cube stuff. Um, yeah, v actually depends, right? Let's not go into that. You could write it differently, I think. Well, okay, think about it. V is completely dependent on the R value. So you could use that thing to get some stuff done, right? Okay. Or maybe first of all, we should just, let's just do the thing. So V is equal to square root of Gm upon R. Just put that in there. So you got negative alpha square root of Gm to the power of 3 actually. So Gm square root of Gm upon R power 3 upon 2, I think. Right? That's equal to this guy. So some stuff cancels, this cancels. Oh, and it's, yeah, that M is still going to be there. No big deal. So it's negative alpha square root of Gm that is equal to, we got this small m dr upon dt upon 2 r power 2 minus 3 upon 2, I think, which is just 1 upon 2, right? So it's basically negative. Okay, let's be, yeah, okay. 2 alpha square root of Gm upon small m dt, that's just equal to r power negative 1 upon 2, I think. And then dr. Is that correct? Probably is. Okay, so let's integrate. So you got negative 2 alpha square root of Gm upon m times the time required for it to fall down is equal to, okay, just equal to, so divide by 1 upon 2 is going to be 2. R power 1 upon 2, right? Okay. Initially, what's the radius? Where did that go? Okay, whose radius is eta times that of the moon's radius, right? And finally, it's just the moon's radius. Call that radius as n. Sorry, no, r, right? Why did I say n out of? Okay, so the radius is capital R, the moon's radius. So it's gonna be r power 1 upon 2 square root of r basically. Minus now, right? Here it was just eta r, so there we go. Square root of eta r, and yeah, this should work out. So 2 alpha square root of Gm upon m times t, that's just equal to 2 square root of r times square root of eta minus 1. This 2 cancels. Yeah, that should give the thing. So t is just m square root of r times square root of eta minus 1 upon alpha square root of Gm. Right. This looks good. And anything else is given? Process of motion, the satellite experiences light, resistance to, right, resistance force to be dependent on the velocity of the satellite. I get that. Find how long satellite will stay in the orbit until it falls or moves. I got the stuff, but do you, I mean, you didn't actually give us what is known and what is unknown. So is R known? Well, whatever, I'm just gonna report this as a final answer. Right, this is the amount of time that you have to wait before it crashes. Next, let's go to 228. 27. Fine. Calculate the orbital and escape velocities for moon. Compare the results obtained with the corresponding results. Look, I don't have the masses and anything. So how do you expect me to solve this? How, like, this is weird. How do you expect me to solve when I don't even know how massive is moon? What's its radius? Just leave it. 29. A spaceship approaches the moon along a parabolic trajectory, which is almost tangent to the moon's surface. At the moment of maximum approach, the brake rocket was fired for a short time interval. Okay, so you got a spaceship. This is the moon. Okay, it is approaching the moon along the parabolic trajectory, which is almost tangent to the moon's surface. What? The moon's surface? This is weird. Okay, so it's like this. Okay, and what are they saying? At the moment of maximum approach. What do you mean by that? Maximum approach? The brake rocket was fired for a short time interval, and the spaceship was transferred into a circular orbit of the moon. Okay, find how the spaceship velocity modulus increases in the process of braking. What do you mean by the maximum approach? I think what you mean is that dr upon dt is just maximum, right? So for that to happen, your d square r upon dt square, that should be 0, right? And it's a parabolic trajectory. Oh, yeah, I don't know how to solve for parabolic trajectories. This is one of the foci. Okay. So the eccentricity approach is what? 1. That makes it a parabola. So your V minimum, which is square root of GM, yeah, all that stuff. We can do it, no big deal. This is still weird, isn't it? So V minimum is approaching 0. V maximum is approaching infinity. What? No, how can that be? It's like square root of GM upon A, and oh, also A value. This thing is actually going to infinity as well, right? So A changes, only the focal length doesn't change because, yeah, okay. Actually, it does change, but yeah, we know the focal length. That's important. So the focal length is, well, in this case, actually, I shouldn't even say it's a focal length. What is this? Yeah, it is the focal length. This is the pole. This is the focus. It's not in okay, whatever. So that's just equal to a times of 1 minus e, right? And this thing is kind of a constant, and everything else is going to, yeah. So a is approaching infinity, e is approaching 1, whatever. Um, cool. So we can just say, first of all, actually do some stuff. So our v minimum, that is equal to square root of, hey, what if instead of doing this thing we just went for this equation that, oh, I don't get it. I don't think it's a good idea to do this thing. But when have you got the maximum approach? So have you ever been on a graph and you just zoomed out and you saw how the parabola looks? So parabola up close it looks like this. Then when you go out, it looks like this. And when you go very um, right, so when you zoom out really hard, it actually just becomes something like this. So it basically becomes like a line, you could say, right? Yeah, and as you keep going far away, like this is actually gonna approach some kind of, you get the thing, right? You get the thing. Yeah, its slope is ever decreasing, isn't that right? Because y is equal to 4ax, so y is equal to, or let's just say y square equal to x for now. So just an example, y equal to square root of x. The slope y dash is just 1 upon 2 square root of x. Right, so as your x increases, the slope is decreasing, and after some point x becomes very big, and this actually becomes kind of like 0, right? So yeah, this actually becomes, let's not say horizontal. Okay, it does become horizontal. What can you even do about that? At that point, of course, your vibe is really, really big, right? This is weird. So then, how do I do this thing? Uh, when will you actually have the highest R dot value? That will happen whenever your R double dot is 0. But when does that happen? Hey, when your R double dot is 0, that just means that omega square R is equal to the centripetal acceleration, right? Oh, interesting. And the centripetal acceleration is just provided by the gravity. Oh, so that's why. Okay. Oh, that explains everything. That's why if at that particular point you switch off the r dot value, so you make that 0, then it's gonna stay in a circular orbit. Okay, that's understandable. Fine, but how do you actually get what that r value is? Because we do have to figure out what that is, right? Ah, find how the spaceship velocity modulus increases in the process of braking. You have to figure out the r dot value. But how do I model this thing? What equations do I use? Maybe this one will be better to use. So a e power I theta upon 1 minus. I don't think that's a good idea. Maybe not. Just wait a second. Yeah, let's forget to do that. Anyway, since it's a parabola, why don't you just think about it as a parabola, right? Who cares? Just start from the basics. You can do that, can't you? Yeah, I mean, it's weird. It's really weird, actually. And every single moment you have to figure out the velocity, which is hard to do, really. Think about it. You can parameterize the position with respect to this pole, sure. Or you could parameterize with respect to the focus, then you're just gonna have this thing, a power I theta upon 1 minus cosine theta, right? The theta is the angle. Uh, yeah, sure. You know what angle I'm talking about. So this is theta is equal to something, and then this is actually theta equal to pi. So the angle that it makes with this axis, that's what theta is. Okay. And now what? So once you got this thing, um, you would want your r dot to be maximum. How do you get the r dot value? Of course, just differentiate this thing and you get something. Right. So once you just solve for that equation, you'll get at what theta value this happens. And what was a once again? Your a was come on, remember it was basically just the lattice vector, right? No, what was it? It was the distance between the focus um, and the directrix, but that times the eccentricity, right? So basically like a times 1 minus e squared, which is, yes, it's just the whole, it's just the half the lattice rectum, because it's a b square upon a square, so it's like b square upon a, half the lattice rectum. In this case, lattice rectum is 4a, so it's going to be 2a basically, right? Because, yeah, yeah, a times 1 minus e is just the focal length, you could say that, uh, right? So it's a focal length, and then you got a times of 1 plus e. Oh, that A is gone, sorry. Okay, you just got 1 plus E. And E is actually going to, and this A, by the way, is different than that. Oh, this is getting confusing, isn't it? So the usual standard formula for parabola, that A is not this thing. This A is the one used in ellipse formula, right? Okay. And if you understand what I'm saying, you understand. Otherwise, whatever. It's the focal length times 1 plus E is just 2, so 2F, right? So you can actually write this thing as 2F times all this. And then, yeah, 2F. F is just the R moon, right? So 2R basically. That makes sense. So you got this as, yeah, okay. And now you got this in terms of theta. Okay, interesting. And now what? So for what theta value do you have R dot equal to maximum? Like, let's do it. So let's do it. This is our R vector value. I know I'm using complex numbers. You don't like complex numbers. I've used it everywhere throughout my journey. So I'm going to use it right now as well. So the velocity vector, playing a different, yeah, differentiating this thing. Hey, could we actually simplify? Because this is, we can write this thing as 2 sine square theta upon 2, and then the stuff, and nah, just leave it like that. Who cares, right? So v vector, first of all, differentiate this guy. So like 2r I e power I theta upon minus cosine theta. And then you got theta dot and everything, right? Mhm. Interesting. You got omega about this point. Okay. And then you differentiate this other stuff. So 2r e power I. You're still gonna get omega, but now you differentiate this thing. So what you have, just have 1 minus cosine theta square. You have a negative because of that, then the derivative of negative cosine is sine theta. So that in there. Okay, so let's recombine. It is 2r e power I, 2r omega e power I theta. And then what do you have? And also actually take this thing common, so 1 minus cosine theta square, right? And now what do you have? You got iota times 1 minus cosine theta, right? And then negative sine theta. So negative sine theta plus iota times 1 minus cosine theta. Does that look good? I think it should. Uh, yeah, it does look good. Okay, there's a problem with all of this because you're going to get this omega stuff, and I don't like it, right? I don't want this to be having omega and whatnot. Hmm. We want this to be a function of time and not this thing, right? Yeah. Hmm. How do you make this a function of? I've never calculated this stuff for a parabolic trajectory because I never had to. But now I have to. And how do I do this thing? When do you have dr upon dt being maximum? Of course, r double dot is 0. It's got omega square r equal to the gravitational acceleration. Sure. But how do you solve that actually? I have no idea. Okay, you got the velocity vector. Just take a right. Just take dr upon dt from here. Don't go for the imaginary part or okay, the tangential part. The radial part only involves this stuff. So dr upon dt is just equal to negative 2r sine theta upon 1 minus cosine theta squared, or let's say negative dr upon dt. That's equal to this guy, right? So when is this the maximum? For what theta value is this the maximum, right? Yeah, actually now it's a good time to convert this from there to there, right? So it's like 2r 2 sine of theta upon 2 cosine theta upon 2 upon 4 sine square of theta. Oh, sine square is already there, so like sine power 4. I don't think that was a good idea. Whatever, just keep going. Hopefully we'll get somewhere. So you have to maximize this stuff. Uh, what is this? Cosine theta. Cos theta upon 2 as alpha for now. So cosine alpha upon sine cube of alpha. Why is that thing? This looks bad, doesn't it? It does. Oh god. You will have to take a derivative with respect to alpha and equate it to 0. I don't want to do that. You have to just do this thing. So you got negative sine alpha upon sine cube alpha. Then you got take the derivative of that guy. So you got negative 3 sine alpha upon sine power 4 alpha, and take the derivative of that guy. So you have cosine alpha 1 sine, so cosine square alpha. This has to be equal to 0. So you got negative sine square alpha, negative 3 cosine square alpha. Is that right? Yeah, it's right. That's equal to 0. Wow, that doesn't look good. Something, I messed up something, right? Yeah, I definitely messed up something there. That is negative, I get that. And where did I mess up? Can't even seem to find that. Simple over there. Wait, I mean, what I'm going to get is something like, it's always positive. This won't happen. It will never be actually equal to 0. So there is no point of maximum approach, which is to be expected, right? Yeah, it is. But then this guy's claim is just wrong, because if there is no such point, then you can never have a circular orbit. Then I must have messed up somewhere. Where exactly? When is this the maximum? Come on. We could just limit ourselves for some particular theta values. We will just say theta goes from 0 to pi. So then theta point 2, it's an acute angle. So then you're asking when is this the maximum, right? Because then that's when negative dr upon dt is maximum. So yeah, right. Oh, okay. So in the first quadrant, as you go from 0, so as you're going from infinite far away point to this point, yeah, as you go like this, when does this become the maximum? As you go like this, your cosine value increases and your sine value decreases. Okay, so this is supposed to become bigger than, right, right, of course, because theta point 2. So what is happening? At pi, we have to reach over here. But at this point, there is no approach at all. It's just 0. And at this point, there is an approach. Okay, at least. At this point, you have the maximum value, and it's actually infinite. Because, wait, what? It's infinite. Now, how could that be? That doesn't make any sense. How can that be infinite? Because, well, it is infinite. But the R value is so big, so your V value must be, yeah, it must be the smallest, right? It's the slowest at that point. How can it be infinity? Doesn't make sense. No, something's wrong. Uh, come on. Oh, there's this omega factor that I left out. You have to look for that as well. So yeah, now let's do it correctly. So you did all of this stuff, but there's this extra omega factor that you should take into account. And is this the maximum? And actually let's start using theta upon 2 instead. So like this. Okay. Oh no, it's gonna give us alpha and whatnot. This is not nice. You will never be able to figure out when this is the maximum approach. Cause yeah, like you will actually have to figure out the velocity and r value at every single moment. How do we do that? There isn't a function to get this thing done. Come on, think about it. What if at infinity this guy's velocity is actually not zero? It's something positive. And then okay, speed is always positive. But what if it is not zero? Then it's gonna speed up, speed up, speed up, and then does this thing. Okay. Yeah, well, actually, that looks right. Right. Wait a second. If you use that stuff, so when you get the V min, you just have square root of gm upon 8 times 1 minus e upon 1 plus e, right? But then, you know, yeah, this thing can actually be written as square root of gm, and then a times 1 minus e is just f. So a is f upon 1 minus e, right? So it's just say r because the focal length is r in this case. So you got r, and then it's going to be 1 minus e squared upon 1 plus e. Now this thing actually goes to 0. So yeah, at infinity it will be 0. So that's at least good. And yeah, right. So now our job is to figure out at this point what is its velocity. It's of course moving in this direction. Right. That is guaranteed. No big deal. Just have to figure out how much is the velocity. Yeah, and then you will have it. Actually, we also have to figure out at what time it will reach there. So that's another complication. Wait, how can we do that? Because it's going from infinity to this point and then it starts off at zero velocity. It's going to take forever to actually come over here. So you can't use time to get the thing done. Oh, you could do this thing. So you start off at here and figure out. So you start counting from this point and then figure out at what time it will reach over here. That we can do. No big deal, right? And what was our Vmax once again? That would just be square root of gm times 1 plus e and all that stuff. So like gm times 1 plus e upon the focal length, which is the radius. So sort of 2 gm upon r. Oh, that's like the escape velocity. It is escaping, of course. So just barely escaping. That makes sense. That's a nice thing. I could write a whole, yeah, I could write a whole note about this. But anyway, right now, this is all we care about. So yeah, let's not use that parametric form. Let's use the standard parametric form for this thing. Okay. So at this point, your V is, I'll just say U, because this is the only fundamental velocity we'll be using. So it's square root of 2gm upon r. Okay, cool. Right. And actually, just for our convenience, I'm going to draw it like this thing. So this is how it should be. Okay, like this. That should be doing it. Now I know that actually want everything centered around the focus that is the center of this planet, but I will intentionally make it like this because that's the form that I'm most familiar with. So cool. And then yeah, just want this r value. That's easy because that's just the directrix distance from this point. So it's just x plus a. Okay, x plus r because a is r. And here the a is one used for parabola. Right. So at this point, x comma y, which, you know what, let's parameterize this correctly. So 80 square comma 2. Let's not use t for this because, yeah, you don't want to be using t for this. AK square. So rk square. Why am I using t right now? Rk square comma 2rk. This distance, like this is actually x equal to negative r. So your small r value, that is going to be equal to rk square plus r. That's awesome. So the potential energy at that point is just, oh, actually we just figure out what's the potential energy difference. So gm or potential difference, doesn't matter. Then you got 1 upon r minus this bigger radius, this 1 upon r k square. We just want some kind of relation between k and time. Okay, that is equal to, so this thing is equal to what, u. Okay, the change in, right, the u actually is supposed to be decreasing, so that makes sense. Yeah, you will have a smaller velocity at that point, sure. So it's just half, and then you got some velocity minus u square, right? Perfect. So v square is just equal to 2gm upon r minus 2gm upon r times of k square plus 1, right? But that thing plus u square, and the thing is u square is just uh, 2gm upon r, so this is going to become, yeah, it's going to become that. Okay, something's weird about this. Am I sure? No, it's wrong. This should not be the thing. It should be u square as I thought it. Yeah, okay. Now this will be correct. So it's negative of this thing and positive of that thing in that case. And u square is just gm, sorry, 2gm upon r. So there we go. Perfect. V square, you got the thing for it. So V square is just equal to 2gm upon, which is to be expected because it was 0 at infinity. And now the radius is this thing. So that works out perfectly. It still escapes, right? So V square equal to 2gm upon r times of k square plus 1. Perfect. So our speed, that can be thought of as, um, wow, square root of 2gm upon r. We should just say it's u, okay, u upon square root of k square plus 1. So now we need the time required to go from this point to that point, right? So v at different k values is given, and we also need the ds path. So the ds path, like you got the r, sorry, you got the r vector value, just figure out the dr. So this will just be r times of 2k comma 2 basically, because yeah, and then you got dk, right? That is your r vector value. So the magnitude of this thing is just a 2r square root of k square plus 1 times dk, right? That's our ds. Isn't that awesome? Because the thing is that you still got this sort of k square plus 1 factor everywhere, so that works out. And now all we have to do is just ds upon v, that will give us our dt. Perfect, isn't it? I would say it is perfect. It's got 2r upon u, and then it's k squared plus 1 times k. This is our, oh wait, it's supposed to be dt, I'm sorry. This is our dt, just why am I taking so long for doing this? Because it's a new question, of course. Actually a nice one. So we want to integrate this thing to get our time from k is equal to 0 to some k. Okay, so 2r upon u, and then this is k cube upon 3 plus k, right? Perfect. This is our time required to reach at that particular point. That makes sense. Uh, yeah. So, oh, but this is still bad because you couldn't get k in as a function of t. If you would have got that thing, it would have been perfect, but you didn't. Mm-hmm. That's not right. This is not. This is not going good. Oh no. You got the time, sure, but you don't have k as a function of time. So, huh. I don't like this. Now, how do I write the, oh God, I just wanted to write R as a function of time, but now I can't even do that because it's not a function of time in the first place. It's a, this equation, do we have any solution for this thing? We don't, because it's a cubic. Even a trigonometric relation would be doing, right? So maybe we do have a trigonometric relation. Who knows? Let's actually try it out. So you got k cube plus 3k. Okay, no, no, that's just wrong. You can't be doing that. Why? Why did this happen? I was going good and now suddenly I'm not. Ah, not nice. That's the as the function of that. Yeah, it is. It's just that bad. So You got time as a function of k, but not the opposite. This is awful. Okay. Hmm. Still, you could try doing it, you know. So since you have t as a function, right? You could think of t being a variable quantity. I know it sounds very weird, but let's do it. So you got time like this. Okay, awesome. And also our r value that's given by it's a function of, where does that go? Right, that's given by this thing. So r vector is given by r times k times k comma 2. All right, that's perfect. I really thought I would get an actual function. I didn't get any actual function, but whatever. So you got the r value. You first of all need a dr upon dt value, right? Hey, so isn't dr upon dt just the x component? Why didn't I think about it? Oh, well, yeah. The basic property of this parabola is the fact that this distance is the same thing as that distance. So if you want our dr upon dt to be maximum, that's basically also saying that our dx upon dt is the maximum. Yeah, because this is decreasing by the same rate as this is decreasing. So, And when is your dx upon dt maximum? That is at x equal to infinity. Wait, no, okay, no. That at that point your v is 0. So it's in the same direction as the x-axis, but it's not the same, right? Okay, so you still want your dx upon dt to be 0 or something like that, right? So there we go. That's our thing. You want your dx upon dt to be 0, sorry, to be the maximum, and your x value is really just, so it's like k square comma 2k, and that's why just want this value, right? Of course, you want to maximize this value. Sorry, the rate of that. So it's 2k. Okay, x is what? X is our k square and t is given to us like that. So we want dx upon dt at what k value it will be the maximum. That's actually just a polynomial function. So you can do this thing, okay, a rational function, whatever. So this thing is like 2k, that r will cancel. We don't have to worry about that. 2 upon u and the derivative of that guy, which is not that bad. This is k square plus 1. Awesome. So this is going to be u k upon k square plus 1. The thing is, this is a constant. This is just equal to u upon k plus 1 upon k. But we know k plus 1 upon k is bigger than or equal to 2, right? So this thing is actually less than or equal to u upon 2. So that is when you will have the maximum value. And when does that happen? At k equal to 1. So it's at the latest rectum that you get the maximum approach. Wow. This distance is, so from the focus, it's just 2r. Finally, we got the thing. Perfect, isn't it? Okay. So at that particular point, what is your velocity? So you want dv upon dt, right? Oh, for velocity, you should have to, yeah, okay, whatever. Just use this thing instead. No, that's the speed. You want the, wait, you want the velocity. Right. You don't want the acceleration, you just want the velocity. So the x vector, okay, the r vector quantity. So you already got this thing, right? This is just equal to u upon 2. So here's what we found out. We found that k is equal to 1, right? Your r, small r, is just equal to 2 capital R. Perfect. You got this stuff. So your dx upon dt, we figured that out somehow. So it's u upon 2. Okay. What is your dy upon dt? So y is this thing, 2kr. So the rate of that thing is going to just 2r. R cancels, just 2. 2 upon the time rate of this guy, which is 2r. That r cancels, sorry. 2 upon u, and you got this thing, k square plus 1. Why am I doing this once again? Whatever. It's just this guy. So it's u upon k square plus 1, which is u upon 2 once again. So, wow, that's awesome. Yeah, it's awesome, isn't it? So this is also u upon 2. And now we finally know how it changed. And since now it just wants to be going to what? Wait, where did it go? Right. Spaceship was transferred into circular orbit of a moon. Actually, you have to, I think I should record these findings. Where I'll go that t value and r vector value, right? So these two things, these seem important actually. And also the u value because, right, so u is the escape velocity. Perfect. So where do I add this in my formula list? I'm just going to add it right here actually. So before 229 or maybe after 229, right? We don't want all of this stuff. Actually, we might want what v is because that looks like a nice thing. You got the v stuff, you got time for r vector. Perfect. Isn't that awesome? And also u is just square root of 2gm upon r. Okay. Yeah. Now what do we have? It changed from u upon 2 in the x direction and u upon 2 in the y direction to just u upon 2 in the x direction, right? That's the change. Okay, what do you want to find? Find how the spaceship velocity modulus increased in the process. The modulus, why do you want that? And by how? What do you want me to report? Do you want me to find the change in the modulus, or do you want me the percentage change, or what? Oh, come on. Okay, I'm just gonna say the thing. So before breaks, it was u upon square root 2, and now after breaks, it is just u upon 2. Cool? That makes sense? Okay. Actually, let's keep that because, right. Let's delete this because we can figure that out at the moment. Okay, awesome. So these are our general findings for any parabolic trajectory. And then you got some specific findings for this problem. I didn't think this would take so long. This is a weird question. This thing is for any parabolic trajectory. All right, perfect. And for this question, just got this as the answer. Actually, you know what? When 229, just do it after this box because then I can talk about it in context. Yeah. Just got this as the stuff. Okay. So k is equal to 1, small r is equal to 2r, whatever. And before breaks, this was the velocity modulus. After breaks, this is the velocity modulus. So there we go. This is our answer. Okay, minimize this. Right, next question, 230. Which is a spaceship is launched in a circular orbit close to the Earth's surface when what additional velocity has to be imparted to the spaceship to overcome the gravitational pull. So it's a circular orbit to the surface of Earth. So it's just got like square root of g upon r. That's our velocity right now. What additional velocity has to be imparted to the spaceship to impart? Sorry, has to be imparted to the spaceship to overcome the gravitational pull. What do you mean by overcome? I mean, just increasing the velocity by itself will do it. Of course, it will make your d square r upon dt square non-zero. It will make it positive, right? So I think what they mean by overcome gravitational pull is of course escape onto infinity. That's like this going from this to square root of 2 gm upon r. So square root of 2 minus 1 times the velocity it had, which is square root of gm upon r. There we go. No big deal. And just the radius of Earth, of course. This should do it, right? Yeah. Right, next. 231. At what distance from the center of moon is the point at which, and you just saw what happens when you actually impart this velocity, right? It goes into this kind of weird parabolic trajectory and does this thing, right? So yeah, I don't even have to prove that it will go to infinity. It will go to infinity. We just saw that. Okay, 231. At what distance from center of the moon is the point at which the strength of resultant of Earth's and moon's gravitational fields is equal to 0? Come on, seriously. So it's like proportion to square root of m. Yeah. So r is supposed to be proportion to square root of m. So that this happens. So this is the Earth. This is our moon. Let's say the moon has mass small m. This has mass capital M. Then this point, right, it's over here. This distance will be like k square root of capital M, and this is a k square root of small m, where k is some constant, right? In the end, this constant is just 1 upon square root of m plus square root of m. So this is the point. There we go. And this times, of course, the distance between the Earth and Moon stuff. So why am I saying Moon stuff? As if Moon is a bunch of pieces. All right, this is the thing. What do you want? The Earth's mass is assumed to be this much times the Moon's mass, and the distance between the center of these planets is this many times greater than the radius of Earth. Right, so basically d is equal to 60r, just put that in there, and m is equal to 81, small m is equal to 1. I know it's not equal to that, but whatever. That's the way proportions work. So you got 9 plus 1 upon, oh sorry, 9 upon 9 plus 1. And what do you want? At what distance from the center of moon? Okay, so this distance, which is this basically, right? That's just 1 upon 10. So 1 upon 10d, which is 1 upon 10 times 60 r. So it's 6 r's, 6 radius of Earth. That should be doing it. Next question. 232. Sorry. Yeah. What is the? I mean, this is weird. You got from a question like this to a question like this somehow, right? 232. What is the minimum work that has to be performed to bring a spaceship of mass something from the surface of Earth to the moon? Oh, yeah. Okay, this is actually a nice question. Wait, do I use this thing or what? So you want the minimum work that has to perform to bring the spaceship, right? So from Earth to moon, right? Okay, no big deal. Now that we know this information, I guess we can use that to figure out some stuff, right? Am I sure this? I mean, are we actually going to trust this source? Yes, for sure, or not? Maybe because it could just be hypothetical values. Who knows? Ah, I hate this. Having less data than what is needed. How do I solve this? I know how to solve this, just that I can't because I have not been given any data. Oh, come on. So what minimum work has to perform to bring spaceship from there to there? Right? Just find the change in potential energy. All you actually have to do is you got this Earth. This is our moon. This is our right. What was it once again? 9 is to 1. So this is 9 times that distance, and that distance was just 6r, right, from the radius of Earth. So radius of from the center of moon. So from the center of Earth, this distance is going to be like 9 times of this gap, which is 54r. So this distance from here to here is just 53r. Or actually, no, you know what? Let's do it the proper way. This is 54r. All right. So then you have to move it from there to there. So you need potential changes and whatnot. I don't like this. You just have to move this from there to there, and from there gravity will take over. So that's the minimum work that has to be done, right? Yeah, of course. Wait a second. I'm thinking of something else because, right, it said minimum work. What I'm thinking of is it's gonna, okay, what it's doing is, so what we are doing is getting this object, we are pushing it, and we just push it till here, and then we'll release it, and then it goes down and it crashes with some kind of velocity. That's a problem because, yeah, some of our energy went into kinetic energy of this body. We don't want that. So if we could somehow get back all that work, right, in some way, then that would actually give you the minimum work that has to be done. That's crazy. But what kind of path would be such that this could actually happen? Minimum in what sense? It's completely hypothetically minimum. That would just be the potential at this point minus potential at that point, magnitude of that. Right, stuff like that. Okay. But what if it's the realistic minimum? That is, right, you are somebody on the spaceship, you are using the fuel or something to propel yourself till this point, right, against Earth's gravity, right? And your moon's gravity is supporting whatever. And then after this point, yeah, just crash into the moon. That's kind of cruel. Anyway, which of these two situations do you call the minimum? Oh, this is weird. And moreover, I don't have any data to solve this. So yeah, just skip this question. 233. Find approximately the third cosmic velocity, i.e. the minimum velocity that has to be imparted to a body relative to Earth's surface to drive it out of the solar system. The rotation of Earth about its own axis is to be neglected. What? Related to Earth's surface to drive it out of the solar system. Oh, out of the solar system. Wait, but that means to infinity. What's the big deal about it? Uh, yeah. Like, what is the big deal? What is this? The third cosmic I don't know what this thing is. I know what escape velocity is, but what is this new? Maybe it has to do with the fact that Earth by itself is rotating around the sun, and that thing is rotating around the galaxy, or you get the thing, right? So, oh, this is weird. But you want everything related to Earth's surface, so it is the escape velocity, isn't it? Or is it not? Ah, okay, so 233 is weird. I don't know how to solve this. And 232, I still don't know how to solve this because no values. 233, we'll figure out after a bit of searching. That's it. I'll see you in the next video.